Hello everyone, welcome back to Physics 40C. Today we're going to be taking our first real deep dive look into circuits and basically the different components and how to start solving them. And to do that we need to recap or at least remind you of a very important formula that you guys learned last time, which was Ohm's law. Ohm's law. And so that was V equals I times R. Now, just to remind everybody, V is going to be for voltage with the unit of volts, so V. I is a little bit different because normally we're used to the letters corresponding to what the term is called, but I is called current, and it has the units of amperes, so 1A. So amperes or amps, as they're also called. So that can be kind of confusing, but that's why I like to write it out as often as possible. So I is for current, which is amps, which is so a unit of A. And R is for resistance, which also has a little bit of a funky unit. It's ohms right there, so 1 ohm. And this is also where we get the term Ohm's law from. So voltage equals current times resistance, or V is equal to the units of amps times the units of ohms. So one of the more important equations to know when you're doing circuitry problems is going to be power. Power. And so power, we consider it to be unit of P equaling I times V. And since V equals IR, we can also say it as I times what V equals, which is IR. And that's where we get this I squared R value from. So this is commonly given to us in units of watts. So this requires a little bit of background knowledge or remembering from Physics 40A when we did work, right? Work is equal to force times distance, and that's in units of joules. Well, power from that class was equal to force times velocity, or force times distance over seconds, or t, I guess, in this case. So force times distance over time, so the unit was joules per second. And because of this, watts and joules per second are equivalent to each other. So watts can also be said in joules per second. And so that is why for circuitry problems, you'll usually see it in terms of E, and in this case, E stands for energy, not E field, is equal to the amount of power times the amount of time that is allowed to pass. So if something that has a power output of 5 watts runs for 5 seconds, we can typically say that there's 25 joules of energy that were harnessed there. So these, I would say, are the two of the most basic and most useful equations for when you do circuits. Definitely you'll see more as come up as we get deeper into this topic, but one thing that I wanted to really cover and elaborate on was the concept of resistors. So both of these equations use the concept of resistance, and so you have R here and an R here. And so it's useful and worth it for us to kind of talk a little bit more about that. Let's see, just add a section. So what are these things called resistors? Resistors. So they are a circuit component that when you see circuitry problems will just look like a little jagged line, and usually they'll be denoted by R with some subscript, so maybe R1 here, and have some unit of ohms. So the value of R1 would be, say, 5 ohms. And so we typically use resistors most frequently when we talk about the different rules for circuits that we have. So we have, say, Kirchhoff's junction rule, or you guys have learned it as the conservation of current. So you have a junction here where one wire will, say, split into two. And it's worth noting that you have, at the beginning, you might have a current I and a voltage V, right? So voltage drops across different components. And so if there's no voltage drop, then V's stay the same. So at this junction, there is no component, so there's no voltage drop. And so we have V and V coming out the end here. So going this way. But with I call it the junction rule, but again, conservation of current, you get two different currents coming down each one of these. So you might have I1, so V, comma, I1, and then V, comma, I2. And so in this case, you have I, so I total is equal to I1 plus I2. And then if they were, say, more splits further down the line, you could also sum all of them together to be equal to I. And for this situation, V at the beginning, so we can call it V equals V1 equals V2. So there really isn't a voltage drop across any of these components yet. And so this rule is more commonly seen in reference to parallel circuits. So you might have a battery here with some voltage, a resistor, and then another resistor. And so this junction here is the same as saying this junction right here. So down each of these would be the same voltage drop, so delta V and delta V, right? But coming down this row, we would have I and two different currents coming down it. So you could have I1, and down this row would be I2. So these are parallel circuits, right? So parallel circuits. So again, to recap, the most important things that you know about parallel circuits is at each junction in a parallel circuit, the current splits off and is conserved. So if you add together what splits off, then you have your total again, and the voltages stay the same, okay? And so that leads us to an equivalent resistance. So if I wanted to, say, combine these two resistances into one resistance, R1 and R2 perhaps, it could be REQ for parallel is equal to 1 over R1 plus 1 over R2. And I usually leave the dot 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 in there to say you could add really any other circuit or any other parallel resistors that you have. It can go on from there. So this is for parallel circuits, and so the only other configuration that we deal with in this class is going to be series circuits. And so the series circuit is where we start to talk about Kirchhoff's voltage law or Kirchhoff's loop law. So you might have 5 volts or some amount of volts here, and 2 resistors in series with each other. And so all that means is in order for a loop to be completed, you have to go through all the way through one resistor and all the way through another, right? So in parallel, if we were to look back, there's technically 2 loops to be completed there. I could either go down this first path or I could go down this one. With series circuits, there really isn't an option. You have to go through both resistors. So we could say that this is R1 and this is R2. And so if we remember what Kirchhoff's voltage law was, or Kirchhoff's loop law, we say the sum of all of the voltage drops for a loop is equal to 0. So in this case, say we have voltage drop 1 across here, oops, and a voltage drop 2, delta V2, sorry, it's a little muddy there, across this one, then we'd have to say the sum of the voltage drops for all loops would be delta V equals the voltage source, that's a positive 5 volts, minus delta V1 minus delta V2 equals 0. And so these two voltage drops do not have to be the same. Sometimes they are because they turns out that the equations work out that way, but I would say most often they're not, because it demonstrates the opposite rule to the parallel circuit. So in parallel, let's write it. In parallel, the currents were the thing that changed and the voltages stayed the same. Well, in series, the voltages are the things that change and the current stays the same. So you have I flowing in through this resistor, and then you also have the same I flowing through the second resistor, and back again. I, in this case, does not change. It's the same for both resistors. So that is the main difference between the series and parallel circuits. And so our EQ for series is much simpler to add together. It's just R1 plus R2 plus any more other series circuits that you have. All right, I think that is pretty much all that I wanted to recap for this. Definitely come to sessions and ask questions if you have any. You can also leave questions in the comment section down below. And thank you so much for watching.